Alright, well we're back. Sorry about the video just cutting off in the last segment. I thought I'd be able to get through most of 2 or 3 chapters at once, and that wasn't the case. So I intend to cover the material from chapter 14 now on our review sheet, and I'll tell you a little bit about what to expect on the exam from chapter 14. And I apologize if I'm talking a little more rapidly. I don't want to have the video player cut out on me again like it did in the last case in the middle of the chapter. So I've got the first 4 problems relating to chapter 14 now up on the board ready to go. These would be numbers 8 on the review sheet, 9, 10, and 11. Our first 2 problems, less so problems, more just write the equilibrium constant for these. So we want to make sure we understand what an equilibrium constant is. A KEQ is always an expression of what's going on with the products divided by what's going on with the reactants at equilibrium. So normally we could use concentration to do that, or perhaps pressure. For this type of reaction where everything is aqueous, we're certainly going to use concentration because these chemicals do not exert pressures like gases do. So the Kc for this reaction would have our product, the copper-ammonium complex, as this would be called. All right. Now it has a 1 as its coefficient, so it's only raised to the first power, divided by the reactants, copper and ammonia, which needs to be raised to the 4th power because its exponent is 4. That's a pretty powerful exponent there. If you forgot that, it's going to have a significant impact on the numbers that you might calculate with that type of equilibrium constant. We have a second reaction in number 9. Not much different going on here, except that we have a solid as part of this reaction. And we exclude solids and liquids, if we have them, from our equilibrium constant expressions. That's done because those 2 phases do not change their concentrations during the course of a reaction. So all we have for this reaction then are the products. Aluminum, which would need to be squared because its coefficient is 2, and sulfide ion, which would need to be cubed because its coefficient is 3. This is an interesting one. We'll see more of this type of reaction in chapter 16 after we have our next exam. Okay. All right, question 10 speaks to the 2 different types of equilibrium constants that are most commonly used. For a reaction involving only gases, it's often more practical to express the equilibrium constant in terms of pressures. And so the formula that we have that lets us translate between Kp and Kc involves a factor of RT raised to the delta N, where this delta N is the difference in the moles of gas on the product side minus the moles of gas on the reactant side. So for our reaction here, we have 2 moles of gas on the product side and just 1 mole of gas on the reactant side. Just going by the coefficients here. Okay? So it's a positive 1. The value of R that we're using is 0.08206 atmosphere liter per mole Kelvin. So I'm plugging in my given K, and then I'm grouping R, 0.08206, times the temperature in Kelvin. It's given in Kelvin here, so it's not hard. And then that's raised to the 1st power. Just a note of caution, order of operations, as always applies. The formula groups R and T. You must multiply them first before you raise that to any exponent. Okay? Here it wouldn't matter since they're both raised to the 1st power. So when we take our 5.88 times 10 to the negative 3 times our factor of RT, in this case we do get Kp equals 0.132. Okay. So we get a different numerical value. Question 11 is a question that gets at the comparison of where you might start a reaction, the conditions that you choose in the lab, and where it will end up at its equilibrium point. Okay? And to do that, we compare the Q, the reaction quotient, to the equilibrium constant. We're told the equilibrium constant for this sulfur trioxide reaction is 12. Okay? So the reaction quotient would be calculated in exactly the same way, except the numbers that we would be using in these three positions are not the equilibrium numbers. Okay? They would be what we start with, where we are at one given moment. Now, compounding this problem is that we're told not the concentrations, but rather we're told how many moles of each material we have. So what we need to do is to take the moles of each of these chemicals and convert them to their initial concentrations by dividing by the volume, which is 4 liters in this case. So our initial molarity of sulfur trioxide is 0.1875. It's 0.625 for sulfur dioxide and 0.325 for the oxygen. So we would plug these three numbers in, and this is no longer, again, equilibrium constant, because these are not the equilibrium concentrations. These are the starting concentrations. But when I take my product, SO2 squared times O2 divided by reactant, SO3 squared, I get a Q value of 3.6. So that's where we're at. Now 3.6 obviously is less than 12. So Q is less than the equilibrium constant. And Q will change until it equals the equilibrium constant. So what has to happen to Q? It has to get bigger. K can't change. That's what it is. 12. So this number has to get bigger. How will it get bigger? We'll work backwards. To get bigger, the numerator values need to become larger, and the denominator needs to get smaller. Well, the denominators are reactant. We can decrease the reactants by moving some of them over to the product side, by literally reacting them into the products. So to answer the question, what's going to happen to the sulfur trioxide? SO3 will decrease, so that SO2 and O2 will both increase. And it'll be a little bit of a change. We'll shuffle a little bit more over to here until these two rise a little. This one goes down, and until this ratio becomes 12 that we've looked at. Okay? So that's how we use the reaction quotient. If we had gotten a number that was larger than 12, the exact opposite would have happened. We would have had to move some products, which we have, back to the reactant side to decrease the numerator, increase the denominator, which would have made that value smaller. Okay? So from either side, we move towards the equilibrium constant. Okay, the remaining problems in this chapter deal with the types of equilibrium reaction tables that we were so used to seeing in this chapter. So number 12 looks at the equilibrium of calcium iodate. Much like the compound that I just erased, aluminum sulfide, this is a solid that is dissolving to form aqueous ions of calcium and 2 iodates in this case. So if we consider the K for this reaction, it will not have the solid. It will only feature the calcium concentration and the iodate concentration, which needs to be squared. So to determine this Kc, that's what we're after, we need to know these two values at equilibrium. We can use a table to lay out the changes that we're experiencing. Now, we're told that just some amount of this is supplied. That's not a number, but it's also not important because we're not going to need that number to calculate our equilibrium constant here. But because there's some of it, we know that a certain amount would react away. Before we go too far with that idea, though, we're actually told how much iodate we have at equilibrium. It says that we have 0.011 molar iodate at equilibrium. So we must have increased the iodate by that 0.011. Now that also would have been 2x if I had continued to use minus x, plus x, right, and plus 2x. So that's how I'll determine the increase in copper then, because copper's coefficient is only 1 compared to iodate's 2. Copper will only increase by half as much, 0.0055. Thus it will be 0.0055 molar at equilibrium. Now these values can be substituted in to our equilibrium constant expression. Right? And again, we didn't need to know anything about actually numbers associated with the solid because it's not part of the equilibrium itself. So this gives us an equilibrium constant of 6.7 times 10 to the negative 7. Okay. And we're all said and done with that. 13 is an interesting little problem because it gives us, it looks like a problem that would use x's that we need to solve with the equilibrium constant, but we get the value of our x, as we're going to see, in a different manner. Okay. So let's look at our reaction, PCl5 in equilibrium with PCl3 and Cl2. Everything is a gas in this case. We're given some information about our initial conditions, and then a rather puzzling way to be told what's going on in equilibrium. So we're told we start with 1.07 atmospheres of the PCl5. The next piece of information that we're told is that at equilibrium, the total pressure is 1.54 atmospheres. Well, for gases, you just have to remember this simple rule. Officially, it's called Dalton's law of partial pressures. But what's in this system at equilibrium are some of the three gases. And the total pressure would just be the sum of those three pressures. Okay? So we know that this is going to equal 1.54. Okay, jump back up to our table now. What's going to happen when we begin this reaction? Some of our PCl5 will react, right? That would form an equal amount of PCl3 and Cl2. We're looking at a 1 to 1 to 1 ratio. So these could each be represented by x, and 1.07 minus x. Okay? We cannot neglect that minus x here. We've got no idea what the equilibrium constant is. I know we've done a lot of problems where we do ignore that x, but we can't do it right here because we don't know what the equilibrium constant is. But these three things represent the pressures of our gases at equilibrium. So I can bring them down here. That's a very simple algebraic expression now that lets me solve for x. This minus x here and this plus x would cancel out, and we'll actually be left with 1.54 equals 1.07 plus one more unit of x. So x is 0.47. You can bring that back up here now and actually get numbers. This will be 0.60 atmospheres, and each of these would be 0.47 atmospheres. You're now ready to calculate the Kp. It's the pressure of your products. divided by the pressure of the reactant. So that is 0.47. Go ahead and square it because they're each 0.47. Divided by 0.6, then that is 0.37 as the equilibrium constant, the pressure-based equilibrium constant. Okay. Now we can only do this type of problem with gases actually, because they're the only thing who add so nicely. We can't do that with molarities and concentration. That's kind of a special case right there. All right, question 14. As I read question 14, the first thing that catches my eye, I've got my reaction N2 plus O2 to produce 2NO. Everything is gases here. The first thing that catches my eye is that the equilibrium constant is small. 1 times 10 to the negative 5th. So I'm already thinking that means not much reaction happens. We don't move much stuff from the reactant side over to the product side. Okay? So if we begin with 0.75 molar of each reactant, the question is how much nitrogen monoxide do we have when our equilibrium is established? Right? Well, some amount of each of these reactants will react away, an equal amount because they have equal coefficients of 1. The coefficient of NO is 2x, or 2, so we will produce double that amount over here. So at equilibrium, nitrogen monoxide will be 2x, and now, because of this small equilibrium constant, I am going to ignore the minus x relative to these starting concentrations that we're given. Right? So they're going to be still pretty close to 0.75, close enough that it's going to simplify the math at least for our solution. Now the Kc for this process would have the nitrogen monoxide concentration squared divided by both N2 and O2. All right. 1.0 times 10 to the negative 5 equals then 2x squared divided by 0.75 squared. Okay. Since both of these are 0.75. So our 4x squared, when I square both the 2 and the x, I'm going to bring this over to the other side now, is 5.625 times 10 to the negative 6. I'll divide by 4. 1.41 roughly times 10 to the negative 6. Then I'll take the square root, and x is 0.0012 molar. Now you're not quite done because nitrogen monoxide is represented not just by x, but 2x. So it's 0.0024 molar at equilibrium. Or 2.4 times 10 to the negative 3 would be a different way of expressing that value. Our last question in this relating to this chapter's material uses the same reaction now, a different equilibrium constant because it's at a different temperature. Remember that the equilibrium constant always changes with temperature. Okay? And this one doesn't even involve an equilibrium table. We're just told 2 of the 3 equilibrium conditions and asked to find the third. Okay. So we know that at this different temperature, the equilibrium constant is 4 times 10 to the minus 4. And then we're told how much nitrogen and oxygen we have. But we're not told the NO concentration. So we can simply solve for that. It's the one unknown. You know, there are 4 numbers here, and we know 3 of them. So we can easily find that 4th value. So our NO concentration squared, at least, 4 times 10 to the negative 4 times the 0.28 and the 0.38 is 4.256 times 10 to the negative 5. Then we'll take the square root of both sides. And the NO concentration is 6.5 times 10 to the negative 3 molar at this condition. Okay? We don't need to, you know, since this follows up on this previous example, we don't need to do any 2x. This wasn't solving for x. This was actually solving for the nitrogen monoxide concentration right there. Okay? So that wraps up the questions from chapter 14. So let me tell you a little bit about the exam then related to chapter 14. Of the multiple choice questions, and I mentioned in the last video, there are 20 overall multiple choice questions. Only 4 are going to come, I think 4 from chapter 14, with a strong emphasis on Le Chatelier's principle. That is, how does an equilibrium adjust itself, or a reaction adjust itself when it is stressed? Okay? The temperature is changed, or one of the concentrations of your reactants or products is changed. Okay? So that's really a lot like the Q versus KC problem that we just did a little bit ago. You would figure out when you're shifted away from equilibrium temporarily due to that stress, which direction does the reaction need to move to get back to the equilibrium constant? And you could do that by figuring out the Q. Did Q get too big or too small, and thus it has to, or again, decrease or increase to become the K again, right? Aside from those multiple choice questions, you should expect to see 3 problems relating to equilibrium constants from chapter 14. Things to be on the lookout for, you know, there are only 2 types of problems. Use equilibrium information, or find it first with a table to get the equilibrium constant, or use the equilibrium constant, like we have here, to find the equilibrium conditions. Look out for the size of the equilibrium constant. That may help you with the approximation method. All right? And again, I stand by my promise that you should never end up with an equation that has x to the 3rd or x to the 4th power with all the middle terms, in other words. So you can solve a quadratic. You have the quadratic formula on your formula sheet. So that's certainly fair game. But if you end up with something that's x cubed plus an x squared plus an x and a number, you've made a mistake. You've probably missed something that helps you simplify that problem. That most likely would be the size of the equilibrium constant. Okay? Of course, also fair game from that chapter are KP, KC relationships, all right, and a whole variety of problems with setting up reaction tables. Okay? So that's what you should be on the lookout for chapter 14. And when I get back on camera next, we'll talk a little bit about what to expect from chapter 15.